Watch a car drifting through a turn or an athlete launching into the air. Predicting where they will end up requires translating that physical chaos into a rigid mathematical framework. Physics functions as a coordinate-based translation system. Once the physical world is mapped onto a grid, algebra performs the heavy lifting. The process begins with the simplest translation, a 1D number line. We observe a single particle moving along this straight axis. To define its state, we attach two distinct vectors to the particle. Velocity represents the current change in position, while acceleration dictates how that velocity will change. When both vectors point in the negative direction, they work together, pushing the particle further along its path. If velocity is positive while acceleration remains negative, they fight each other, pulling against the motion. A rigid coordinate system eliminates intuition-based errors. This systematic mapping creates the foundation needed for all complex physics. Relying on the word deceleration often leads to errors on exams. It is an unscientific term that obscures the actual mechanics of motion. The 1D safety net relies on two specific rules. First, if the velocity and acceleration vectors point in the same direction, the object speeds up. Second, if the vectors point in opposite directions, the object slows down. A negative acceleration does not inherently mean an object is slowing down. It indicates the vector's direction relative to the chosen grid. Acceleration is a directional translation. Its mathematical sign is determined by the grid, regardless of whether the object is gaining or losing speed. Translating motion into visual histories reveals an object's progress through geometric proof. This involves three foundational graphs stacked in a hierarchy: position, velocity, and acceleration over time. This x versus t plot shows a continuous curved path. Because the position does not change at a constant rate, we know the velocity is changing. Stepping down from position to velocity requires taking the slope, the geometric equivalent of a derivative. Stepping up from acceleration to velocity requires calculating the area under the curve. This area represents the integral, providing displacement data. A specific trap occurs when reading a velocity time graph, specifically the moment the line crosses the horizontal axis. This crossing signifies the exact moment an object stops and reverses its physical direction. Translating these graphs decodes an object's history and future. The solution comes from the logic of calculus, not rote memorization. Two-dimensional motion introduces a core paradox: an object dropped vertically versus an object fired horizontally from the same height. Why do both objects reach the ground at the exact same millisecond? Stroboscopic photography provides physical evidence. In this image, a dropped red ball and a horizontally fired yellow ball are captured at identical time intervals. Despite the yellow ball's horizontal travel, their vertical coordinates match perfectly at every step. Analyzing this motion involves treating it as two independent 1D scenarios occurring in perfect orthogonal isolation. In the horizontal dimension, acceleration is 0, resulting in a constant horizontal velocity. In the vertical dimension, the acceleration is a constant negative g. This causes the vertical velocity arrows to lengthen over time, while the horizontal arrows remain identical. The vertical and horizontal components are independent. The only variable shared by both dimensions is time. Through the concept of orthogonal independence, complex curving trajectories seamlessly resolve into the basic 1D rules applied separately to the individual axes. Moving from theory to practice requires a consistent protocol: strategize, execute, and evaluate. The strategize step requires defining the origin and the positive direction before assigning any numerical values. This involves extracting implicit data. A phrase like starting from rest must be translated strictly into the constraint that initial velocity equals 0. Next, the execute step utilizes the 4 core constant acceleration kinematic equations to solve. To select the correct formula, identify the missing variable you do not have and do not need. By eliminating equations containing the unwanted variable, you isolate the single equation needed to solve for your target. Execution is a process of systematic elimination based on the initial translation of the physical scenario. The evaluate step serves as a final check to catch translation errors. Dimensional analysis confirms that the units resolve to the expected outcome. Finally, the results must pass a physical reality check. If a calculated value violates common sense, it signals a misplaced decimal or a sign error. Kinematics remains the translation layer between the physical world and coordinate geometry. The process spans from the 1D number line through calculus-based graphs to independent 2D components. When a physical scenario is rigorously translated into a coordinate system, the mathematical solution becomes inevitable.